Hello, my name is Silvana Yala Pelaez, and I am a bifacial PV analyst at NREL. Thank you for joining the Bifi PV workshop. Today, I will be giving updated field test results for our 75 kilowatt field single-axis tracking array here at NREL. Here's the outline of this talk. First, some motivation and site description, followed by performance results. We have some neat results on edge effects and shading mismatch measured in our field. We will conclude with some modeling results and takeaways from this ongoing project. At NREL, we've deployed a 75 kilowatt 10-row single-axis tracker system with a mix of bifacial and monofacial modules. The motivation behind this field is to be able to have a representative field of a large-scale array, where we are also comparing bifacial modules to monofacial modules with the same type of cells. So we have a true side-by-side comparison for some of the technologies. Each row has a different technology. We have 4 rows of PERC bifacial and 1 row of silicon heterojunction, as well as 3 rows of PERC monofacial, doing side-by-side comparisons so we can measure the bifacial gain. Some of these modules are from the same manufacturers, so we're able to have a direct comparison of the bifacial versus monofacial module with the same cell type. We're doing string level monitoring as well as module level measurement, which enable us to look at non-uniformities in power production throughout the field. And finally, we have deployed various irradiance sensors throughout the rows, both for front and rear facing plane of array irradiance, as well as albedometers. The main difference in modeling the performance of bifacial systems is obviously the inclusion of rear irradiance on the back of the system. Standards for measuring the performance of a module, as well as modeling tools, have been updated to account for this additional rear irradiance by combining it with the front irradiance. Now, the efficiency of the back of the module is lower than the front, and this is captured on the bifaciality ratio. The 4 PERC technologies we have on our field have a bifaciality ratio between 65 and 75%, with a module nameplate between 350 and 375 watts. The silicon heterojunction row has a higher bifaciality ratio of 90% at a 400 watt nameplate. Prior to installation, each module's front and back performance at STC were measured with a SPIRE 4600 instrument. The table at the bottom shows the variability in the measurements on the module IV curves from one module to another for our technologies. Results to date for the NREL bifacial testbed are shown here, which includes 12 months of summary data for one silicon heterojunction string with a bifaciality of 90% and an average of 3 p-type PERC strings with a bifaciality of approximately 70%. Cumulative NREL results indicate a bifacial energy gain of 7.4% for the PERC modules and 8.4% for the silicon heterojunction modules. The field study includes periods of snow and low temperatures in October and to February. In particular, February was very snowy, which are indicated here by the increased bifacial energy gain due to the reflective snow. Also, during winter months with ambient temperatures below 10 degrees Celsius, the gap between PERC and silicon heterojunction performance decreases, owing to the difference in module temperature coefficient. This provides a performance advantage to the silicon heterojunction string at high but not low operating temperatures. And here's one example of 2 snowy days. As we can see, measured plane of array irradiance for front and rear are shown here on red and blue, respectively. On the first day, which is cloudy, you can look at this at the ground horizontal irradiance in the albedometer, the rear irradiance sensor is actually measuring more irradiance than the front POA. And the second day, it starts cloudy, but then the irradiance increases. We can see this reflected in all of the modules' power production. The bifacial modules, here highlighted in blue, are producing power, low but producing during the cloudy, snowy day, compared to the monofacial. The next day, though, it's more interesting. There is some ground horizontal irradiance light available since early, and it seems that the bifacial modules are able to start producing power and shed the snow much earlier than the monofacials, which start coming online later in the day. Snow is fun. It also covers your sensors. Here we can not see our three albedometers, a CM22, an apogee pyranometer, and an IMT reference cell. So we installed three different albedometers on the side to be able to compare their measurements. And there are some spectral effects taking place. The reference cell, for example, tends to overpredict albedo on snowy days, while the broadband sensor has a slightly higher measurements overall on other days with lower albedo. Also, it's not only spectral effects at play, but in many days we noticed that the reference cell shape, which is square and boxy, collects faster and sheds slower the snow on top of itself, compared to the more round design of the other sensors. But talking specifically about the spectral effect, the spectral mismatch has been researched with more detail by Michael Ghostin and Bill Marion on a paper presented at the recent PBSC. By comparing the ground reflected irradiance from data of the SRRL from a pyranometer to a reference cell, they found that spectral effects are up to 15% for snow relative to brown winter grass and 10% between green grass and summer grass. Besides the albedometers, we have rear irradiance sensors throughout the field. We've looked in particular at this set of rear irradiance measurements, 4 of which are reference cells across the plane of the module from east to west, as well as 2 broadband irradiance sensors, a CM11 and a pyranometer. These sensors are located in the center of row 3. On the left, we can see that the 4 rear-facing reference cells along the collector width of the module indicate much lower rear irradiance values in the center of the module than the edges. The cumulative variability from the start of the experiment until mid-March shows a variation between 8 to 13% from the average. Now, for the same period, on the right, we have the broadband pyranometers, which are exhibiting an additional 20% increased response relative to the reference cells. I wanted to highlight some of the ongoing research to better understand the rear irradiance and our modeling of it by Mark Monarch. Mark implemented a has-been modeling on our high-performance computing, the rear irradiance on our bifacial array field to validate it with our data, but modeling it with full spectral detail for the sky, the ground, and other materials in the scene. He has achieved a very close match with our measurements with the different broadband sensors in our field, which each has a different spectrum response and thus predicts different levels of irradiance as seen in the previous slide. We also studied the variability of the power from module to module according to its location in the field. To do this, besides the string monitoring, each module has module electronic monitoring. We aggregated the data from January to May of this year and then normalized all the rows by the average field production. By doing this, we can immediately notice which ones are the monofacial rows we're using for comparison in our array, rows 3, 6, and 8. And although there's a lot of variability caused by the module electronics monitors themselves, we can still see when we look at the rows the edge effect. Here is a close-up of row 7. Each rectangle represents one of the modules, with the bottom of the heat map being the south edge of the row, which perceives more reflected light from the sun. The north module is also seeing increased irradiance, but not as much. And the increased irradiance translates to an electrical mismatch between the modules in the row in the range of 3%. Another interesting experiment going on at this field is this custom module shown here. We refer to it as Hydra module due to the fact that this module has 12 rows of 5 cells, each with a junction box at each side that can be accessed. This allows us to make measurements of current along the module's length. To give you another representation, here is the electrical design of our custom module, the 12 rows of 5 cells, each with the junction boxes. Field data were collected in the tracker field, indicating that spatial distribution of current loss reaches 6% for one of the months. As the title of this presentation suggests, we are making data from the bifacial field publicly available. There is currently 10 months of data in Excel and Python pickle format at the Duramap Data Hub. The user manual describes the site and the data with the column headers, units, and description. Bifacial rows 2 and 9, performance string level data as well as module level data is included, and performance data for a monofacial string as comparison. There are also a number of front and rear radiance sensors in the plane of array, albedo data on site, and weather data from the NREL Solar Radiation Research Laboratory, SRRL, which is co-located at the NREL campus. The direction address to access this data is down here. Now, I'm going to briefly cover a few tools that we can use to model bifacial system performance and energy gain, which we applied to our field. Some of the softwares can calculate power output for a bifacial field, like SAM and PVSYST. We also looked at predicted irradiance with two of our bifacial irradiance models developed at NREL as open sources, bifacial B-factor and bifacial radiance. Although we're still investigating the reasons, we found that models, in particular B-factors, are underpredicting rear irradiance for our site. In particular, we found that models underprediction is more pronounced under high albedo and high albedo high DNI conditions, like the ones shown here on the third and fourth day. We are even using accurate ray tracing simulation models, although they have similar underprediction relative to actual field measurements. There are many possible causes: forward scattering of direct irradiance, which enhances the upper and ground albedo, spectral effects, higher than expected light transmission through the gap between the modules. We are still trying to assess what exactly is contributing to this model error and whether it is dependent of the type of ground cover or other factors. Here I'm showing measured versus model irradiance for the front and the back in SAM, the System Advisor model, for the period of July 2019 to March 2020. As we can see, there is a better match for the front irradiance than from the back, with that underprediction being present. And taking the modeling one step further to power, here we have measured and modeled yield for one of our rows for 2 days in the winter. The day on the left has low albedo of 0.2, and the day on the right has high albedo of 0.8. Measure and model results for the monofacial string are shown here on the left, accounting for the measured IV parameters from the factory data. Agreement is between a 9% model over prediction. However, DC power optimizer losses are not currently considered in the performance model and will contribute 2% absolute to the model overestimate. On the right side, we have the bifacial row comparison. In this case, we're having a 7.5 model over prediction. This is 1.4% less than the overprediction of the monofacial system, and likely due in part for the DC loss from power optimizers and other factors. Additional analysis can help us assess some of the other sources of model error. We've particularly seen low performance relative to the model, particularly at low irradiance conditions. This could potentially indicate an incident angle modifier coefficient that is too small, or loss from the solar edge DC power optimizers, which have reduced efficiency at low power. Other incorrect assumptions of module parameters in SAM description of the PV module might include temperature coefficient. The remaining 5% offset error under high irradiance conditions is likely a DC offset in the model, such as wiring loss or DC insertion loss, or perhaps slight LID performance loss after the module left the factory. The causes of this model and prediction are still being investigated, but are somewhat consistent with the conservative assumptions of the rear irradiance models in the B factors. But as we pointed before, measuring front and rear plane of array irradiance can predict the performance very closely, making it important to measure this in our bifacial fields. Now, I'm short on time to go over this slide in much detail, but learning through the process of deciding and operating this field, we have some takeaways regarding sensors, handling of the data, and other details that might be useful if you're thinking of setting your own bifacial large-scale testing site. In conclusion, bifacial PV has become mainstream, with more and more projects being installed. Here I presented results from our one-axis tracker validation looking at energy gain of our modules by technology, PERC versus silicon heterojunction, looking at edge effects with our module level monitoring, and also shading effects. I also presented results on irradiance measurements, both for rear, plane of array sensors, and albedometers. And finally, comparisons between model and predicted irradiance and performance with various softwares. Thank you so much for your attention, and if you have any questions, here are our emails.